So here we want to approximate the relative extrema of this function right here, and we are allowed to use technology to help us. So for the extrema, we need the derivative. So the first derivative would be something like 3/2 x squared minus cosine x. And we set this equal to 0. So we have 3/2 x squared minus cosine x equals 0. So what we can do is on Desmos, we can graph that equation, which is going to give us a graph, and then we consider the x-intercepts of this graph. And I would recommend that we graph in radians. So per Desmos, if you graph this on Desmos in radians and you look at the x-intercepts, they are about plus or minus 0.711. So this is where the derivative is horizontal. So look, the graph of the original function, who knows what kind of crazy function it is. It's some sort of composite function where you have like a cubic added with a trigonometric. Who knows what kind of crazy thing this is. But the derivative has zeros here. So what you do is you go to a number line and you make cuts at the number line at all of the critical numbers. The critical numbers are where the derivative is 0 or undefined. For this problem, the derivative was 0 here at these locations. So at negative 0.711 and positive 0.711, we make a number line, not for f, but for f prime. And then what you do is pick test values that live in each of these respective intervals. For example, between here and here, I can test the number 0. Over here, I can test the number 1. And over here, I can test the number -1. So I'm going to test -1. I am going to test 0. And I am going to test +1. When I say test, I mean take these numbers one at a time and plug them into the first derivative. And all I want to know is, in return, do we get a number that's positive or negative? So let's see. So this basically means f prime of -1, f prime of 0, f prime of 1. Plug in these numbers into the first derivative here on a calculator and see if you get back a number that's positive or negative. It should be the case that if you plug in -1 into the derivative, that you get a positive number. The number itself, who cares? It's positive. When you plug 0 into the derivative, you should get back a negative number. The value, who cares? It's negative. And then here it should be positive. So in your f prime number line, we have positive, and then we have negative, and then we have positive. So these test values have served their purpose. I'm going to dismiss them before I accidentally think that they have any more benefit to us, because they don't. The only thing that matters now are these numbers. So remember, the first derivative is like the slope of a tangent. Here the graph has a positive derivative, which means that the tangent line is going up. Here, the tangent line is going down because the derivative is negative. And then here the derivative is positive, so it goes up. So look, what happens generally speaking? Let's say this is the graph of f. What happens if you go up and then you go down? You have here what we call a local maximum. What happens if you go down then up? You have what we call a local minimum. I know that I'm going up, down, down, up based on the sign of the first derivative. Here we're going from positive slope to negative slope like this, which means that there is a max. There is a max at x roughly equals negative 0.711. And similarly, we have a minimum at x roughly equals 0.711. Let me say a couple more things before I let you go. So this should really be called a local or a relative max, a relative minimum, because it's not the absolute maximum or minimum per se. It's just a local maximum, a local minimum at these locations here. If you want the actual point, like the coordinates, you'd have to take these x values and you'd have to plug them into the original function to get their respective y coordinates. I'll let you do that. Let me look at the directions again. It says approximate the relative extrema of f for part A. That's really vague. I don't know if they want ordered pairs, x comma y, or just the x's. I don't even know if they want you to round. So I'll leave it to you to decide what to do from here. But as is, these should be the relative extrema. Watch, check it out. So in the first box, I typed in the original function and then I called it f of x. In box 2, if you type in f prime, it'll give you the graph of the derivative right away. And if you click on the zeros of the derivative, that's what we found in the video, right? We used the graph of the derivative to see the x-intercepts. Now, what I want you to see is that the math we did is legit, because on the graph of the original function, that is what you call your local max, and it occurs at this x value. That's your local min, and it occurs at this value. These were the y coordinates, by the way. And if you overlap it with the original function, you see that here, the maximum of the original function is in line with the zero of the derivative, because they occur at the same spot. Similarly here, the minimum of the original is in line with the x-intercept, the other x-intercept of the derivative. So it all ties in together. Kind of cool. So let me know if you have any more questions.